Recall that the rank of a matrix and the nullity of that matrix are related. We summarize this result in the rank-nullity theorem. So let's let A be a matrix with m rows and n columns. Then the rank of matrix A plus the nullity of matrix A is equal to the number of columns of matrix A. So this relates rank and nullity of a matrix, but we've just extended the concepts of rank and nullity from a matrix to more generally a linear transformation. It turns out that this same rank-nullity theorem can be extended also. So the rank-nullity theorem for linear transformations is almost the same. Let T be a linear transformation from a vector space V to a vector space W. We define n to be the dimension of vector space V. Okay? Then the rank of the transformation plus the nullity of the transformation is equal to the dimension of the vector space. This new rank-nullity theorem extends the old rank-nullity theorem in a way that's completely consistent with the old one. So this just says the same thing but more. It says everything the old one did, but just gives more information. Okay. So let's prove this. I think the proof is quite elegant. Okay. We know that the image of T and the kernel of T are subspaces. So the image of T is a subspace of W. Every subspace has a basis. So there exists a basis for the image of T. And we can write that basis of the form TV1, TV2, and so on. Okay? I want to make sure we understand this point because they kind of skip right to it. So if image of T is going to be a subspace of vector W, okay? So a basis of image T would be vectors in W. So maybe W1, W2, and so on. Maybe that will be our basis. Okay? But we also know these vectors are in the image of T. That means that there is a vector that I can transform to get here. So there is some vector in V, so that TV1 equals W1. There is some vector in V such that TV2 equals W2, and so on. R. Okay? So we can find some basis of this form for the image of T. We could do the same thing with the kernel, right? The kernel is a subspace of vector space V. So we're going to pick a basis for the kernel. So we could take a bunch of vectors, U1 all the way to US, that form a basis for the kernel. Okay? So they tell us the punchline, what we're going to show right here. Now, we want to show that the basis for the image of T, the number of vectors, and let me rephrase. We want to show the basis for the kernel together with the pre-image of the basis of the image of T. Those vectors together, the U's and the V's, form a basis for V, and that would actually show this result. Because the rank of T is just how many vectors are in the basis for the image, right? And so V1 to VR, V1 to VR, that's the rank, okay? R in this case. The nullity of T is just the number of vectors in the basis of the kernel, U1 to US. So there'd be S. So the nullity would be S in this example. So we're saying that if we put those together, U1 to US, V1 to VR, that forms a basis for V. N is the dimension of V. So N should be this many vectors, how many vectors we have here, plus however many vectors we have here, S plus R. All right? This is how many vectors we have in the kernel. This is how many vectors we have in the basis for the image of T. Okay? So that's kind of what we're going to do. If we could show this, that will get us 99% of the way there, in other words. Okay? So in order to show that this is a basis for vector space V, we start with an arbitrary vector V in vector space V. Vector V could be any vector in vector space V. Okay? Since vector V is in vector space V, that means T of V would be in the image of T, right? If we take the transformation of something in V, it takes us into W, into the image. That's what it means to be in the image. So since this is in the image of T, we can express this as a linear combination of the basis of the image. Okay, so some constant times the first vector in the basis plus some constant times the second vector in the basis, and so on, until we get to the last constant times the last vector in the basis. Okay, so what we're going to do is we're going to subtract this over to the other side to get this equation. And then because our transformation T is a linear transformation, I can move all the scalars inside the transformation, and I can, every time I'm adding a transformation of two vectors, I can move the addition inside the transformation. So I could write it all as a single transformation of these vectors, of this sum of vectors. Okay? And it's equal to the zero vector. What do we say about when we get the transformation of a vector that's equals to zero vector? Well, by definition, that means that the vector we're taking the transformation of is in the kernel. Remember, the kernel of the transformation is just the set of all vectors that when I take the transformation of it, it gives me zero. Well, I'm taking the transformation of a vector, and it's given me the zero vector. Therefore, this vector here is in the kernel of T. Okay, this is in the kernel of the transformation. But we have a basis for that transformation, or we have a basis for the kernel, don't we? The vectors u1 all the way to us, that is a basis for the kernel of transformation T, which means I can express any vector in the kernel as a linear combination of these vectors in the basis. Okay? So here I have a vector in the kernel. So I'm going to take that vector that's in the kernel of T, and I'm going to express it as a linear combination of the basis vectors of the kernel of T. So some constant, some scalar constant times u1, plus some scalar constant times vector u2 all the way to my last scalar constant times my last vector in the basis of the kernel of T. Okay? So we're going to do a little more algebra. We're subtracting all this. Let's add it to the other side of the equation. That's going to give us just vector v all by itself on one side of this equation. So now I've expressed vector v as a linear combination of both the vectors v, v1 to vr, together with vectors u. Now remember, there was nothing special about this vector v. It was any vector v in vector space v. And we showed that with no other assumptions, we can express vector v as a linear combination of vectors v1 to vr together with u1 to us. Which means that vector space B must be equal to the span of those vectors. Okay? Yeah, any vector in V, we just showed right here that we can express it as the span of these vectors. Okay? And all of these vectors live in vector space V. And a vector space is closed under addition, closed under scalar multiplication. So any linear combination of these vectors would also be in V. So we do have equality here. Okay? All right. So remember our goal. We wanted to show that that set of vectors is a basis for vector space V. We've done half the work. We've shown that vector space V is equal to the span of that set of vectors. But a basis is more than a span. A basis is two things. In order for a set of vectors to be a basis for a vector space, it needs to span the vector space. We've got that one checked off. But also the set of vectors needs to be linearly independent. That's the next task we have to check. Okay? So now we need to show that that set of vectors is linearly independent. Now remember, the way we usually show a set of vectors is linearly independent. We set a linear combination of the vectors equal to the zero vector and then show that the only solution to that homogeneous equation would be the trivial solution, where all the coefficients of all the vectors have to be zero. So that's what we're going to do here. We take a linear combination of all of the vectors here that are a spanning set for vector space V. We set that linear combination equal to zero. We want to show that all these coefficients have to be zero so that we only have the trivial solution. That would mean that the vectors are linearly independent. Okay? So what we're going to do this, we're kind of going to do it in two steps. First, we are going to apply linear transformation T to both sides. We're going to take the transformation of both sides of our homogeneous equation. Okay? Now, because T is linear, I could break up the linear combination like this. Okay? So I get C1, it moves outside of the transformation, and the sum moves outside, and that's true for every term here. Right? Now, remember the U's. The U's form a basis for the kernel, and anything in the kernel of the transformation of that vector is zero. Okay? So the transformation of U1, the transformation of US, transformation of all the other U's, they're all equal to zero. So all of these go away, leaving me only this expression here equal to zero. Okay? Leaving me only this expression here. But remember, T of V1 all the way to T of VR, that's a basis for the image of T. And remember, a basis, a set of vectors that are a basis are linearly independent. So these vectors here, they're linearly independent. Okay? So since all of these vectors are linearly independent, and we have the homogeneous equation, it must be that the only set of coefficients that we're going to work here is setting them all equal to zero. We have only the trivial solution. So I know all these C1, C2, all the way to CR, I know they are equal to zero. And so that means in my original equation, notice it's the same C1, C2, all the way to CR. Those are all zero. So that gets me half the way there because I know this is zero, I know this is zero, and I know all the other V's are zero because the coefficient has to be zero. So that leaves me with just this equation here. A1U1 plus A2U2 all the way to ASUS equals 0. Now U1 to US is linearly independent. Why? Because again, it's a basis. U1 to US, we assume that is a basis for the kernel of T. And every basis is linearly independent. That's part of what it means to be a basis. So these vectors are linearly independent, and I've just set a linear combination of those vectors equal to 0. The only solution here, the only choice that we can make for A1, A2, AS is setting them all equal to 0 because those vectors are linearly independent. We have only the trivial solution where all the coefficients are 0. So A1 to AS all have to be 0. And so we're done. We started by showing that all of the C's, all of these coefficients have to be 0. And then once we had done that, we showed that all of the coefficients A here have to be 0. And so this linear combination here, being set equal to the 0 vector, it has only the trivial solution. which means these vectors are linearly independent. So we conclude that this set of vectors is a basis for V. Okay? And that proves the result because U1 to US, that is a basis for the kernel. Okay? So there are S vectors in the dimension for the kernel. So this is S. And then V1 to VR, that is related to a basis for the image of T. Notice V1 to VR is not the basis for the image of T. TV1 to TVR is, but it's the same number, right? So the dimension for the image of T has to be R, just like this is R. And so if I take these vectors together with these vectors, that's a basis for V. The dimension of the basis, N, is just how many vector, I'm sorry, the dimension of the vector space. The dimension for the vector space V is equal to N. And the dimension is just how many vectors are in the basis. So that's just going to be S vectors here plus R vectors here. So S plus R equals N. This is the nullity. This is the rank of T. And so that proves the results. The rank of T plus the nullity of T is equal to the dimension of the vector space.